Mr. B. Dhanasegar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science, and here we have the subject that is theory of computation. So let me start with what we had seen as far as the previous episode of the same subject is concerned. The context-free grammars. If you are given the context-free grammar, first of all we must ensure that the grammar is in the simplified form, and for ensuring that the grammar is in the simplified form, we must first of all eliminate the useless symbols from the grammar, and once the useless symbols have been removed out of the grammar, then we can find out whether there is any epsilon production available in the grammar or not. So those productions are used in the grammar only for generating empty strings. So if you are very sure that the language L does not include any epsilon, that is empty string, then we can simply eliminate the productions which are nullable or which are of the form A derives alpha or A derives alpha in multiple number of steps. So there is a need for finding the grammar symbols which are capable of deriving empty string, and they must be rewritten in such a way that they will never generate empty string. One more thing is, we may have the productions of the form that is A derives B, where both A and B are variables. So in that case, they are valid production rules, but they will increase the number of steps available in deriving strings rather than making any change as far as the language recognition power is concerned. So more the number of productions of the form, that is unit productions are there, definitely it will take more number of steps in recognizing a string. So after doing all these three steps, we can ensure that the grammar obtained is going to be simplified grammar. So once the grammar has been simplified, then we can go for normal forms. There are two normal forms available. One is going to be the Chomsky normal form, and another one is going to be the Gribach normal form. So we will call it as CNF and GNF. So the general format of both CNF and GNF we had already seen in the previous episodes. So if you want to say that the grammar, that is context-free grammar, is available in CNF, then there are only two possible forms of the productions. One is A derives BC, where B and C are variables, and another one is A derives small a, where small a is on the right hand side of the production. So either there should be two variables on the right hand side, or there should be exactly only one terminal available on the right hand side. So such a grammar is sufficient in order to generate any context-free language. So when we are finding that only these two forms of productions are appearing on a grammar, then we can claim that the grammar is available in Chomsky normal form. But most of the time we may not be having grammars, or when you are converting the language specification to context-free grammar, we may not be able to directly come up with these context-free grammars in Chomsky normal form. So there is a need for converting the given grammar into the Chomsky normal form, because there is an advantage in going for the Chomsky normal form. First of all, the grammar is going to be, the production rules are much simpler, and the parse tree whichever we are converting, constructing for the strings from this grammar will be always binary nature. Because when we are expanding a variable, definitely there will be two branches, and if it is going to be a terminal, then that is going to be leave node. So we can very easily construct the parse trees with only binary tree implementation rather than going for n-array tree implementation. So not only that, the number of steps required for deriving the strings, provided the grammar is in Chomsky normal form. So that is also going to be another factor. So it is going to be fixed. For a string of length that is L, so what is going to be the number of steps required for deriving the string? So that is also going to be fixed. But if the grammar is neither in Chomsky normal form or in Gribach normal form, then there is no guarantee that the number of steps required for deriving a string will be known in advance. But here in the case of Chomsky normal form or in Gribach normal form, we can assure that the number, we can very easily find out how many steps are required for deriving a string of length L are going to be n. Let us start with the conversion of the given grammar into its equivalent, that is Chomsky normal form first of all. So first we must ensure that the grammar has there is no epsilon production and no unit production and no useless symbols in the grammar. So first you find whether it is going to be of the form B, C or A or not. So if the each production in the grammar, context free grammar G is of the form A derives BC or it is going to be only A, then you can simply ignore that because it is already in CNF. Because the format of each production in the grammar in CNF form is going to be only A derives BC or small a. Since already the productions are of the form A derives BC or A, then we can simply leave that. And suppose if the productions are not of the form either BC or A, then what should be done is, first we have to replace every terminal A in the production by a new variable called C, and once you introduce the new variable called C, we must introduce a production rule for that, where the production rule is of the form C derives small a, where small a is on the right hand side, for which we are giving the replacement capital C. So not only adding, that is replacing the small a by C, but introducing the new production C derives small a is also very important. If you do not include the C derives small a production into the grammar, then after replacing this small a by capital C, then the C becomes going to be an non-generating symbol. So to avoid that, we must include a new rule called C derives small a. So once it is done, every production, if it is not already in CNF, now they are all of the form A derives B1, B2, B3 etc. up to Bk, and finally that is where the condition is k is going to be greater than or equal to 3. So if k is 2, it is already in CNF. If k is 1, it must be only a terminal because it cannot be variable since we have already removed the unit productions. So k is 1, you just ignore that, and k is 2, you just leave it, and once we find that k is greater than or equal to 3, then we must ensure that the grammar must be rewritten in such a way that it is going to accept the properties of context free grammar in CNF. So now how do you do that? So if it is going to be the production, that is A derives B1, B2 etc. up to Bk is a production, then we must introduce k minus 2 number of new variables. So we can introduce the new variables called C1, C2 etc. up to Ck minus 2, and now we can go for breaking the production A derives B1 to Bk into smaller productions. So when we are having k number of symbols, so we have to find out how many number of new symbols to be introduced. It is going to be k minus 2 number of new symbols to be introduced, and for every k minus 2 number of symbols, we must introduce productions in addition with the starting production for A. So we will be having k minus 1 number of productions in total when you are breaking a production of the form A derives B1, B2 etc. up to Bk. So how do you do that? It is first you start with A, you introduce B1, and for this B2 to Bk we are introducing a new variable called C1. So that C1 is once again is going to be expanded. So with production rule, that is C1 is, it is starting with B2, and B3 to Bk we must give another new variable. So that is going to be C2. So suppose if k is only 3, then introducing C1 itself is sufficient, because C2 becomes B2 and B3, we can stop that. But in general, first it is going to be A deriving B1 C1, and then C1 is B2 C2, then C2 is going to be B3 C3, so keep going, and the last production to be included is Ck minus 2 is deriving Bk minus 1 followed by Bk. So these are the last two variables available in the grammar. So since two variables only available on the right hand side, we can claim that this production is already in CNF. So So, this is what the the procedure for converting the given grammar into its equivalent CNF. So, now we can see an example, that is how we are finding or the converting the given grammar in the, that is your given context free grammar into the equivalent grammar in Chomsky normal form. So, here is the example. First of all, we are finding whether the grammar has any useless symbols or not. So, if you have any useless symbol, then they can be completely eliminated out of this grammar. So, here we have a grammar with some number of useless symbols. So, first you see that S derives AB or CA is the first production rule, then B is having this, then A has small a, C has A followed by capital B or B. So, to remove the useless symbols, we have actually two steps. One is going to be the identification of the generating set, and then followed by the identification of reachable set. The generating set is including the set of all symbols which are capable of generating strings of its own. So, by default every terminal is capable of deriving a term, that is a string. So, we start with small a, then small b, they are the only two number of that is terminals. So, a and b are included in the generating set. Now, we have to find out the productions of the form, that is some a derives alpha, where this alpha contains only terminals from the generating set or only symbols from the generating set. So, what happens is this a becomes a generating symbol and this capital C becomes a generating symbol. Since a and C becomes generating, because of the CA on the right hand side of S, S is also generating. So, now we find that except B, this is except capital B, all the symbols are generating. So, now we include only the productions where B is not there, that is capital B is not there. So, we will be having S derives CA and AB is not going to be part of the resulting grammar because of B is not going to be generating symbol, and then A derives small a, then C derives small b, these are all the productions available as output. The next step is finding the reachable set. So, for reachable set we will include the starting symbol of the grammar in this set first of all. Then for every production for this S, you include the every symbol available on the right hand side of the production into the reachable set, because once we have reached the left hand side of variable, it is possible to reach every symbol available on the right hand side of the production. So, S is reachable means we can say that A and C are reachable, A is reachable means small a is reachable, and C is reachable means small b is also going to be reachable. So, we will be having S, capital C, capital A, then small b and then small a. So, the resulting productions are S derives CA, A derives small a and C derives small b, and the language is going to be B followed by A. So, this is how we are eliminating the useless symbols available in the grammar. So, now to convert the grammar into its equivalent CNF, so here we have an example, that is we are having S, where the right hand side is capital A, capital S and B or epsilon, and then A is A, capital A, S or A, and for B also we have three production rules. So, we do not find out any kind of useless symbols as far as this example is concerned, but we have epsilon productions. So, once you are finding the epsilon productions, so they can be eliminated, and here we find S is nullable. So, since S is nullable, we must include the that is we must apply the algorithm for the elimination of epsilon productions. So, we will be having S is A followed by S followed by B, and another one is AB, because the presence of S and absence of S. So, that is why we are having two productions for S here, and S is available even on the right hand side of capital A also. So, for capital A we are having A followed by capital A followed by S, first one, and the absence of capital S we will be having A followed by capital A, and already there we have a rule called that is A. So, we will be having A derives small a. So, A derives A, capital S, and A derives small a followed by capital A, and A derives small a. So, now as far as B is concerned, so we have that is S, B and S, then A, then B. So, we shall see that conversion of how we are eliminating the that is epsilon symbol that is how we are eliminating the nullable production from this grammar after a short break. So, welcome back. We are seeing the example where the elimination of useless symbol have been done, and then we have seen that how we are eliminating the epsilon production. So, the second case of the production is going to be B is S derives S B S. So, this S either present or absent, similarly this S either present or absent. So, we will be having there are 3 number of production rules, SBS with both the S's are available, and the first S is absent here, here the second S is absent, and if both S's are absent, then we will be having small b. In addition with that, we are having capital A and then followed by small b, small b. So, this is what your new set of production rules after removing the epsilon productions. Now, we have to study how we are converting this into the equivalent Chomsky normal form. So, first you have to find out whether every production in the grammar is of the form A derives capital B followed by capital C or going to be small a. But here we find that they are not available in the form, many of the productions are not satisfying that condition. So, what we should do is that is just follow the algorithm whatever we have studied earlier in order to that is find out the grammar in CNF. So, wherever we find that there is only one terminal, leave it, and wherever we find that only 2 variables on the right hand side, leave it, and if there is any violation, what should be done first is every terminal available on the right hand side should be given some replacement. So, we find that that is, for example, here we have the terminals called small a and small b. So, we are introducing a new variable called capital A with small a as suffix, denoting that this is the variable introduced for the small a with the right hand side containing only a, and one more terminal is b. So, for b we are introducing another variable called a with suffix b, whose right hand side is going to be b. So, once we have introduced these 2 productions, so we can go for that is replacing the small a available in the right hand sides as well as small b available on the right hand side with capital A followed by with the suffix a and capital B with suffix b. So, here we have the there is new grammar after replacing the terminals by the corresponding variables. So, first one we do not have any kind of problem because A is B, and second one is also no problem. But when you are having the third one, that is the production for capital A, we found that there is a small a was already there and followed by capital A's. So, for the small a we have given a replacement called capital A with suffix a, and here also with the same thing has been done, and here we have a small b. So, for the small b the replacement is capital A followed by with the suffix b, and even here also the small b has been replaced by capital A with suffix b. Same thing is also done here, and here the small a has been replaced by capital A with suffix a, and here the small b, both b's, that is b followed b is no more, it is now a b, a with suffix b and a with suffix b. So, still we find that the there is grammar is not in CNF. We have the right hand sides with more number of symbol, that is either there is 3 number of symbol, that is in that case. So, what should be done is we must convert this into the CNF satisfying the condition that either 2 variables on the right hand side or only one terminal on the right hand side. So, as far as this grammar is concerned, S derives A S B is violating the CNF property, whereas A B is satisfying, and then for A this capital A with suffix A and capital A are satisfying, small a is also satisfying, and as far as B is concerned, we have A B is no problem, we have S A B no problem, B no problem, and A is no problem, small a is also having no problem, and A B even A B is also not having any problem. So, other than these rules, we need to break those rules in such a way that there is exactly 2 number of variables on the right hand side. Let us see that is how we are converting this first rule, that is S derives A S B into its equivalent that is Chomsky normal form. So, first S is deriving capital A, then followed by, since we are having more than one variable on the right hand side other than this A, so we must give a replacement for this right hand side. So, A is deriving that is SB, where this for SB we are giving a new variable called S1. So, this S1 is going to be the left hand side for any there is derivation whose right hand side has only this SB. So, the replacement is you just give S1 here, and then the expansion for S1 is S followed by B. So, the first rule in S is now available in Chomsky normal form. Moreover, the newly introduced rule for S1 is also in Chomsky normal form. So, there is no need of further breaking this production rule to more number of production rules, it is not required. So, now we find all the rules related with S are in Chomsky normal form. Then when you are going for the production rule for A, we find that there is A with suffix A, then once again capital A, then capital S. So, 3 number of variables are available, but we cannot have 3 variables simultaneously on a production rule to call the grammar in CNF. So, there is a need for breaking as such what we have done for S. So, it is going to be AA followed by, we can introduce another new variable called A1, and then this A1 is going to be the pattern or the left hand side of production rule whose right hand side is nothing but this AS. So, we will be having capital A followed by capital A's suffix A and capital A1, and capital A1 is going to be A followed by capital S. So, rest of the productions for A are already available in that is Chomsky normal form. So, A with suffix A, capital A and small a. And when we go for B, once again the first rule is violating the Chomsky normal form property because of 3 number of variables are there, S, A and S. So, there is a need for once again breaking. We can go for introducing a new variable called B1. So, we will be having that is S B1 with the B1's rule is A B S, and another one is going to be B is deriving that is A followed by A followed by S. So, even for that also we are following that is AB, since AS which is already given a replacement that is small, that is capital A1. So, we can go for giving that expansion as that is A1. So, the resulting grammar is now available in this form, here is given, and we find that every production rule in the grammar is already in the form that is of the form that is 2 variables followed by 1 terminal, 2 variables or 1 terminal. So, since every production is available in the form either 2 variable or a single terminal, then we can claim that this grammar is going to be in CNF. So, this is how we are converting the given grammar into its equivalent Chomsky normal form. So, next to that, as far as our conversion is concerned, so we need to go for converting the given grammar into its equivalent Gribach normal form. So, as far as Gribach normal form is concerned, the general format of the productions is going to be A derives small a followed by alpha. That means, the right hand side of every production available in the Gribach normal form grammar should start with the terminal, and followed by that we can have anything. So, if it is going to be a terminal on the right hand side of the production for every production available in the grammar, it means in every step of the derivation of the that is language recognition, one symbol will be definitely consumed, or in every step of the derivation we will recognize one symbol and we will continue further. So, if you are given a string with n number of symbols, certainly with there is n number of steps, it is possible to recognize the string, but that is not true with that is any other there is grammar in any form. So, the main advantage with your Gribach normal form is, so once the grammar has been converted into Gribach normal form, even though the grammar looks very lengthier, or a grammar the more number of symbols or more number of production rules are involved in the grammar, the main advantage there is the number of steps required for deriving the string is going to be always linear with respect to the number of symbols available in the string. So, as far as the conversion to GNF is concerned, the first step is we need to eliminate the left recursion available in the grammar. So, to first you decide whether the grammar is left recursive or not. To say the grammar is left recursive, we have the productions of the form capital A derived followed by alpha or alpha 2 etc., etc. But definitely we cannot have all productions of the form that is capital A starting with the right hand side. We must have some non left recursive production rules also for A. So, if we have only that is or exclusively the left recursive rules, then the grammar is going to be totally that is useless grammar, because it is not capable of deriving any string at all. To say that the grammar is going to be a valid grammar capable of deriving at least one string or more, we must have at least one or more number of non left recursive rules. So, the non left recursive rules are that is A derives beta 1, beta 2 etc. up to beta s. So, given the production rules of this form, the main drawback with this left recursive production rules are, so when you are constructing a parse tree for the given sentence, so what will happen is, if it is going to be a top down parser, so we will start from the root and we will expand. So, every time we will try to expand the leftmost child of the parse tree. So, if we keep on expanding the leftmost child with the very first alternate for the production rule, so the tree will never terminate. So, since because the recursion is available in the leftmost portion, the tree will never terminate. So, that is what we have to eliminate the production rules where the grammar symbol is going to be left recursive. So, now we need to rewrite this grammar in such a way that the grammar has no left recursion. So, how do you rewrite? So, first you have to find out that is the production rules which are non left recursive. The non left recursive production rules are going to be A derives beta 1, beta 2, beta 3 etc. up to beta s, and then we have to introduce the left recursive productions. So, to connect the left recursive rules with non left recursive rules, so what do we do there is, for every beta 1 we will introduce a new variable called b, because we need to connect this alpha 1 also. So, b is going to be new variable which we are introducing. So, beta 1 b, then beta 2 b, and then beta 3 etc. up to beta s b. So, for A actually we got there is r plus s number of production rules. So, now still we are having r plus s number of production rules, but the production rules with left recursions are rewritten in such a way that beta 1 b, beta 2 b etc. up to beta s b are the new set of rules. Then after that we introduce the new rules for b. The new rules for b are alpha 1, that is whatever is remaining as far as the left recursive rules are concerned. So, what do we have is alpha 1, then alpha 2 etc. up to alpha r, these are all the remaining components of this A. In addition with that, so once this alpha 1 has been generated, so what will happen for the connectivity once again? So, if you want to repeat this alpha more number of times, then we will be going for that is introducing b. So, b followed by that is alpha 1 b, then alpha 2 b, then etc. up to alpha r b. So, given grammar as the productions of the form A derives A alpha, and now we have no that is production with A immediately on the right hand side of the production rule. So, A derives A alpha is no more, but still it is possible to generate the same set of strings. Suppose if beta 1 is a string to be generated, straight away you can start with A, expand with beta 1. Or suppose if you find that it is going to be beta 1 followed by alpha 1 to be generated, then first you go for the production rule beta 1 followed by b, then if it is alpha 1, for b you just expand it by alpha 1. So, what we have is now there is A derives there is beta 1 b, in the next step b derives alpha 1. So, we will be having the string pattern called beta 1 followed by alpha 1, that is essential form which is derived from this A. Without having any kind of left recursive issues, we will be able to generate the same set of that is strings. So, as far as the language component is concerned, we do not find out any difference among the two versions of the grammar, whether it is going to be a left recursive one or a non left recursive one. The grammar, even though the two different versions of the grammars are available, we find no change as far as the language recognition is concerned. So, this was the very first step required for the converting the given grammar into its equivalent Greback normal form. And one more rule required for the conversion from the given grammar into its equivalent Greback normal form is the substitution rule. Suppose if you find that there is a variable available on the right hand side, and if a variable is there, certainly there will be a production rule available for that variable. So instead of using that variable as such there on the right hand side of the production, we can replace it by the corresponding right hand side of that variable itself. So when you go for more substitutions, the advantage there is the number of steps required for deriving a string can be reduced. So that is what the advantage. So it is certainly not changing the language of the grammar, but the advantage is the number of steps, because the production rule itself we are doing the substitution, and the number of production rules thus we are getting will be more. But even if you are having more production rules, maybe the size of the parser will be little larger, but certainly it is not affecting the parsing time. So more the production is available or more substitutions we have done as far as the grammar is concerned, it will take less time for parsing. So that is what really needed, because parsing will be done more the number of times than constructing a parser. So for the parser construction it may take little more, but whereas parsing will definitely take less amount of time. So that is what we go for the substitution rule. So having the substitution rule as well as the rule for eliminating the left recursion, we can think about converting the given grammar into its equivalent Gribak normal form. So the procedure for converting the grammar into its equivalent Gribak normal form is, the very first step is going to be the arrangement of the productions of the form in such a form that like ai derives aj gamma where I is less than j. That is, we should find out the production rules where always the low order production is starting with the higher order, that is higher numbered production on the right hand side. But certainly it is not possible to find out always the production rules of this form, because every time a an already encountered variable, maybe this a1 deriving a2 gamma or a1 deriving that is a3 gamma is available, but certainly it is not always of that form. So there is a limit. So beyond which we will find that a high order variable on the left hand side and a low order variable on the right hand side. At that place we will go for substitution, and then we will replace, we will apply the left recursion elimination, and thus we will be able to find out the grammar with that is in the Gribak normal form. So that topic we will study in the next class. Let us summarize what we had seen as far as this class is concerned. So we have seen the conversion of the context-free grammar into the CNF, and later we have just started the conversion from the context-free grammar into its Gribak normal form. So that part will continue in the next episode. As far as the grammar questions are concerned, so first it is going to be, how do we prove that whether the language recognized by the grammar, given grammar is same as the language of the grammar for the equivalent grammar in CNF. So the next one is how we are converting it into CNF. So then what is going to be the advantage in really converting the context-free grammar to CNF, and what is going to be the difference between the context-free grammar in CNF and GNF, and the very prime advantage is the number of steps we are having as far as the recognition of the languages are concerned. So you may have even questions from that component also. How many steps are required for deriving a string of length, that is L, from the context-free grammar in CNF or in GNF. These are the question components as far as this episode is concerned. So with this I conclude this episode. Thank you all.